students, we are learning direct approach for short circuit analysis, and in last two lectures we have seen three types of faults, that is LG fault, line to ground fault, double line to ground fault, LLG fault, and triple line to ground fault, and then we have derived various fault current equations for them as well as post fault voltages for all these three types of faults. Today we are going to see line to line fault. So before going to the line to line fault, just revise what we have seen. So we have seen that in case of line to line fault, we have divided our BC-BV matrix. So in case of direct based approach, we know that we are having this BC-BV matrix and your BI-BC matrix, and here we are having voltage difference with respect to first node, and these are basically nodal current matrix. So, and this BC-BV and BI-BC are calculated based on the connections of the distribution systems and impedances of the distribution system. And in the last class, we have seen that this BC-BV matrices we basically divide into rows, and we have given the names for specific rows. Say if you are considering this particular rows, we have given name for this rows as BC-BV, since it is corresponding to A phase. So, A and corresponding to third node, so 3. So, we have called this row as BC-BV 3A. Similarly, if you consider this row, it will be BC-BV, it is corresponding to C phase. So, I will write C here, and since it is corresponding to 6th node, I will write 6th node here. Exactly similar way we have divided our BI-BC matrix, but column wise. So, if you are considering this column, since it is corresponding to this particular current, that is, then we can call it BI-BC, since it is corresponding to node 4. So, I 4 and then corresponding to A phase. So, I should write A. This how you can calculate, we can give the names for each of the column, and once we do this, we will get this matrix, where these are the rows of BCV matrices and these are columns of BI-BC matrices. If you remember, in last two classes we have derived the various equation short circuit current. So, we have derived that in case of LG fault, that is line to ground fault, your post fault current, and say if the fault is occurring on phase A of ith bus, it will be equal to your Z SC LG and then its inverse into voltage at first bus, and then we have seen that this Z SC LG short circuit for LG fault will be equal to your BI-BC in corresponding to your ith column. So, this particular column, I am considering the fault is occurring on this particular bus here, and sorry, it should be BC-BV. So, this is BC-BV, and then we are having this BI-BC corresponding to ith bus and A phase, plus your ZF is your short circuit of LG fault impedance matrix. Similarly, we have derived for say LLG fault. So, in that case there will be two currents, fault current in phase A, fault current in phase B will be equal to, we have seen that here in this case it is short circuit matrix corresponding to LLG fault and its inverse, and it will be get multiplied with voltages of first node of A phase and B phase, and in this case your Z short circuit for LLG fault is equal to, we have seen it is, we need to take two columns corresponding to BC-BV corresponding to A phase, BC-BV matrix corresponding to B phase, multiplied by, you have to take column corresponding to BIBC, column corresponding to A phase of ith bus, and BIBC column corresponding to B phase and ith bus, and plus ZF, ZF, ZF matrix of 2 by 2. So, it was actually your Z impedance matrix for LLG fault. And in case of triple LG fault, we have seen in this case there will be all the three currents present, short circuit current. So, short circuit current corresponding to phase A, short circuit current corresponding to phase B, and short circuit current corresponding to phase C will be equal to, in this case, your impedance matrix corresponding to LL triple LG fault, LLLG fault, its inverse, and in this case there will be all the three voltages V1A, V1B and V1C, and in this case your impedance matrix will be, this is short circuit matrix corresponding to triple LG fault will be equal to, in this case we need to take all the three rows of BCBV corresponding to that bus, that is BCBV corresponding to A phase, BCBV corresponding to B phase, BCBV corresponding to C phase, and here we need to take columns of all the three phases of BIBC matrix, BIBC of A phase, BIBC of B phase, BIBC of C phase, plus there will be ZF matrix of 3 by 3 size, so this will be your short circuit matrix for triple LG fault. So, we have seen these things in last two classes. Let us go ahead with LL fault. So, in case of LL fault, we will be say this is your distribution system, say this is your ith bus, this is your phase A, and then this is your phase B, and say this is your phase C, this is your ith bus, this is I plus 1th bus, and this is I minus 1th bus, this is your B phase and this is your C phase, and it is part of big system. So, that is why I am showing dot dot here, so that it will be part of any big system. And let us say this is short circuited with B phase. So, A phase is getting short circuited with B phase with say impedance ZF. So, in this case this is current, fault current in A phase, and we have seen that this comma F notation we are using to represent post fault quantities, and this current is post fault current in B phase. So, this particular current is fault current in B phase, and this particular current is fault current in A phase, and we can see that in this case they are opposite in direction. So, if you consider the terminal conditions, so in this case since C phase is not faulted, so you can say the C phase current will be equal to 0, then A phase current will be equal to say post fault current of A phase, and in case of B phase it will be post fault current of B phase. However, we can see that these two currents are in opposite in direction here. So, this current is this in this direction, and fault current in B phase is actually in this direction. So, I can just say this is equal to minus of fault current in A phase. Now, if you see a voltage equation, so you can say voltage difference between phase A and phase B, that will be equal to voltage across this impedance here. So, in this case I can write post fault minus voltage at bus B post fault will be equal to ZF into your fault current in A phase. So, this voltage of A bus and this voltage at V bus will be nothing but the impedance drop across this 2 phases. So, this equation is valid there. Now, if you see this matrix which you have got, where which we have used for load flow calculation, and where we have written all the BCB matrices as rows, and all the columns of BIBC matrices are shown here. So, these are nothing but columns of BIBC matrices. Now, we can see that since the fault, during the fault condition, only these two currents are very large as compared to all other load currents on all the other buses. So, basically all other currents will be getting equal to 0 except these two currents, they will be negligible though. So, we are considering equal to 0. So, all these currents, they will be equal to 0 except these two current. So, this current will be equal to fault current in phase A, and this current is opposite of that. So, that is why this current is fault current in phase A, but it is in opposite direction, that is why minus sign is there. So, basically what we will get is, we will get this equation here. So, as I replaced all the currents here with equal to 0 except these two current which are fault currents, and if you see these two equations, if you write these two equations explicitly, so I am taking these two equations here, and these two equations if I take, it will be V1A minus post fault voltages of A bus and V1B minus post fault voltages of voltage of B phase will be equal to your, these two matrices will come into picture, that is BC BV IA, BC BV corresponding to B phase. And if you see this part from here to here, only this column, these two columns, this one and this one, they are getting multiplied with non-zero quantity, otherwise all other columns are getting multiplied with respect to 0. So, only non-zero will be nothing but multiplication of this column multiplied by your this current and this column multiplied by this current. So, basically it will be equal to BI BC corresponding to A phase, basically this column I am taking, BI BC corresponding to B phase, this column I am taking, and this is getting multiplied with two currents only, that is current in A phase which is this one, and current in B phase which is opposite of A. So, that is why I can put minus sign here. Now, if you explicitly multiply these two vectors, so I can get 4 parameters here, that is BC BV IA, which will get multiplied with respect to this. So, I am just multiplying this vector with respect to this vector. So, there will be 4 terms. This is your first term, which is multiplication of this and this. Then if you multiply this with respect to this, I will get another term, that is BC BV IA multiplied by BI BC IB, and if you multiply this term with this, it is BC BV corresponding to A phase and BI BC, sorry, corresponding to B phase here, BI BC corresponding to A phase, and fourth element is BC BV corresponding to B phase and BI BC corresponding to B phase. So, you have got these 4 parameters of this matrix, and these two currents are as it is. Now, to express it matrix in short form, I am calling this as Z I AA corresponding, because BCB also A part is coming, BIBC also A part is coming. So, this impedance part I am calling it as ZAAI, this part, these two terms I am calling ZIAB, this part I am calling ZIBA, and this fourth part is actually ZIBB, and it is getting multiplied with this fault currents A and B phase, but they are in opposite direction. That is why only one current I have written with minus sign. Now, let us take these equations on next slide. So, we are having these two equations, V1A minus V1B minus post fault voltage of V phase, which is equal to, we have divided this matrix into 4 parts, that is AA, ZI AB, ZI BA, ZI BB, and we have seen it is getting multiplied with respect to fault current in A phase and fault current in B phase, which is opposite of A. Now, let us subtract this first or subtract second row from this first row. So, this is first row, this is second row. So, subtract second row from first. So, if you do this, it will be V1A minus post fault voltage of A phase minus V1B minus post fault voltage of B phase. It will be plus minus minus plus, it will be equal to, in this case if you observe this matrix, this is actually symmetric. So, ZIAB will be equal to ZIBA. So, in this case if you subtract this first row from second row, it will be ZIAA into fault current in A phase minus ZIAB into fault current in A phase minus BA into fault current in A phase plus fault current in A phase. And then we can write this equation, it will be V1A minus V1B, I am taking it together, and we have seen that this subtraction, here we have seen that this subtraction of post fault voltages of A phase and post fault voltage of B phase is nothing but impedance multiplied by your short circuit current. So, from this we can easily write this subtraction is nothing but minus ZF into fault current in A phase. So, this minus this will give you ZF multiplied by fault current in A phase, and in this case we can take this fault current common out, and applying this condition it will be ZIAA. So, minus twice of ZIAB plus ZIBB, it will be getting multiplied with your fault current in A phase. And from this ZF we can take on the right hand side. So, I can write V1A minus V1B will be equal to ZIAA minus twice of ZIAB plus ZIBB plus your ZF into fault current in A phase will be this one, and we are basically interested in calculating this one. So, we can easily write fault current in A phase will be equal to inverse of this multiplied by this current voltage vector here. So, it will be ZIA minus ZIAB plus ZIBB plus your ZF, and you need to take inverse of it multiplied by your voltage of A phase and voltage of B phase at first bus. And as I told you, voltages of A phase and B phase at first node, they are known. These matrices are known because they are getting evaluated from BIBC and BCB matrices, which are actually known. So, you can get your fault current here. So, this is equation for, so this we have got Z short circuit for LL fault. So, this particular matrix I am calling Z short circuit for LL fault. So, let us say if you want to calculate post fault voltages of any buses. Now, to calculate post fault voltages, of any buses other than bus I, because I have considered fault has occurred on ith bus. So, other than I, if you want to calculate voltages, post fault voltages at any buses, suppose you want to calculate this particular bus. So, in this bus, say bus corresponding to nth bus is N and your phase is B, and for that particular bus you want to calculate post fault voltages. So, in this case we need to take this equation here. So, if you take this equation, it will be V1 B minus Vn post fault of B phase, which will be equal to your BC BV matrix. This part will come. So, rho corresponding to A phase and nth bus, which is this, and this will get multiplied with respect to this part of the matrix. And we have seen that this part of the matrix where all these columns of BIBC, they are getting multiplied with respect to G, except these two columns which are getting multiplied with non-zero values. So, this particular two columns, they are getting multiplied with non-zero values. So, I am taking those two columns, that is BIBC corresponding to A phase and BIBC corresponding to B phase of ith bus, and this is getting multiplied with respect to fault current in A phase minus fault current in B phase, and this is basically given. Fault current we have seen, we have already calculated in last slide. So, fault currents are known when we are calculating post fault voltages. So, we can get the post fault voltages. So, in this case this is known, this is unknown. So, I can easily write post fault voltages of B phase of nth bus will be equal to V1B, which is B phase voltage of first bus, multiplied by BC BV of, and then BI BC of B phase, and then A phase. So, this will give you post fault voltages of any bus. So, in collective term I can write this equation. So, for any jth bus I can easily write this equation. So, we are having any jth bus of all the three phases will be equal to your voltages at bus number 1 for all the three phases, which will be minus, and then BC BV matrix corresponding to J phase multiplied by this part of the matrix will remain same for all the calculation, and then it will get multiplied by with respect to this one. Only difference here, I am considering all the three voltages here, means your VJ matrix will be having all the three voltages, VJ of H phase, VJ of B phase and VJ of C phase. Similarly, this V1 matrix also will be having all the three voltages, that is V1A, V1B and V1C, and this BCBVJ will be also having three terms. So, BCBVJ matrix will be having three rows. So, it will be BCBV corresponding to JA, BCBV corresponding to JB and BCBV corresponding to JC. So, all the three terms. So, here we can get for any unknown bus post fault voltages using this particular expression. To understand it better, let us take one example where I consider this system here, which is 6 bus system. However, in some of the sections of the line there are only 2 lines, and in some of the line there is only 1 line. So, in between 5 to 6 only 1 line is there, and then between 4 to 5 2 lines are there. So, here only 1 line, 2 lines, and here all the 3 phase lines are there. So, in this case wherever there are 3 phase lines, there will be total ZABC matrix because all the 3 phases exist. So, ohm per kilometer. So, this matrix multiplied by whatever kilometers of that particular line will give me impedance of that particular section. So, impedance matrix of this particular section. So, for first section we can easily calculate this ZABC multiplied by 6.1 will give me impedance matrix of first section, and similarly we can calculate impedance matrix for second and third section, which are 3 phase in nature. In this particular section between 4 to 5 only 2 phases are existing. In that case you can use this matrix. So, this matrix multiplied by 5.3 kilometers will give me impedance matrix, which is 2 by 2 for section 4 to 5, and for section between 5 to 6 only 1 line is there which is having this particular impedance. So, this multiplied by 5.2 will give me impedance matrix between 5 to and 6. So, we can get the impedance matrices for all the sections of this particular system, and then I am considering the initial voltage of bus number 1, it will be 11.4 kV, and which is 3 phase voltage, and then we are going to consider the fault impedance, which is 0.001 per unit, and in all the 3 cases we are going to consider fault which is occurring at bus 4. So, first step we have seen that first we have to build or we should know the BIBC and BCBV matrices for this particular system. So, if you calculate BIBC matrix for this, which is basically this one, and as I told you we have given the names for these columns of BIBC matrix. So, any column which I can pick will be having some name here. So, this will be say BC BIBC corresponding to, it is corresponding to 4th bus. So, that is why 4th and A phase. So, every column of BIBC matrix will be given names kinds of this, and then we have seen BCBV matrix which will be having the nature like this. In this case also each row of BCBV matrix will be given some name. So, since it is corresponding to bus number 3, so we can say BCBV corresponding to 3, and since it is corresponding to C phase, I can give this name to this bus as BCBV 3C. Like this all the rows will be given name. So, basically when we are considering fault, single line to ground fault which is occurring at this particular bus with fault impedance of ZF, which is 0.001 per unit, and we already know the impedances of all the sections of the line, and from that we have built your BCBV matrix and BIBC matrix. So, basically since the fault is occurring on bus number 4, I am taking an phase A. So, I am taking this BCBV matrix corresponding to bus number 4. So, this is corresponding to bus number 4 and phase A. So, this particular row is BCBV corresponding to 4 and phase A. So, I am taking this row here. Similarly, we will take column corresponding column for BIBC matrix. So, if you take these columns and rows which are basically required for single line to ground fault analysis. So, that particular row of BCB matrix I have taken it here, and column of BIBC matrix I have taken it here, and we have seen that the fault current of bus 4 on phase A is actually given by this particular expression here, and we have seen that this fault impedance matrix is given by this particular expression here, where this is actually BCBV of 4th bus corresponding to A phase, and BIBC matrix corresponding to bus number 4 and A phase, and this is ZF. So, basically we have got these two quantities here, and if you multiply them, so you can see that only non-zero entities will be. So, if you multiply this with respect to this, you will get this, which is basically this is non-zero corresponding to entry corresponding to this is non-zero, and entry corresponding to this, which is non-zero, this one. So, it will be Z12 AA plus Z23 AA plus Z34 AA plus this ZF is already there. So, you can easily get this impedance matrix corresponding to your LG fault for this particular system, and if you put this fault value here, this V1A is already given from this 11.4 kV. You can easily get the phase A voltage of bus number 1. So, this is known, this we have calculated here, this is known. So, we can calculate fault current for phase A of bus number 4. Now, let us consider if there is LLG fault. So, in case of LLG fault, you have seen that we short circuit these two buses with impedance ZF, and we need to calculate these two currents. This current we have seen, we called it as A phase current, and this current which is flowing here, we call it as a B phase current. And both these currents of, so this actually I is 4th here, so I should write 4 here. So, bus number 4 A phase, bus number 4 B phase currents will be given by this particular matrix, which we already derived, short circuit matrix corresponding to LLG fault multiplied by voltages of bus number 1. So, these voltages are known. So, if you know this matrix here, we can easily calculate. So, let us see how we can get this matrix, and we have already derived the matrix for your LLG fault, which is given by this expression here, and if you explicitly multiply this 2 row, we will get this matrices here, and from this particular multiplication you will get these terms. Okay, basically this column and this row and this column we are multiplying. So, basically you will get this quantity here plus ZF is still there. Then BCBV multiplied by BIBC corresponding to A and B phase, you will get this term here, and from this term I will get this term here, and from this term I will get this term here. So, just from these two matrices I have got these 4 quantities into this particular matrix, and once you get this matrix, inverse of this matrix can be put it here to get the fault currents. So, this is how fault currents can be analyzed, and in case of LL fault, we have just now seen, we have divided this matrix multiplication of these 2 columns and these 2 rows into 4 impedance matrices, which you have seen. This is corresponding to AA phase, AB phase and BA phase and BB phase, and from this if you multiply explicitly this matrix with respect to this matrix, I will get these 4 terms like this, and and from this we can derive the short circuit impedance matrix for LL fault. We have just now seen that is given by this particular expression here, we already derived just now, and where this is nothing but, this part is nothing but ZAA of 4th bus, this is ZAB of 4th bus, this is ZBA of 4th bus, and this is nothing but ZBB of 4th bus. And from this, if I am putting these values of ZAA, ZAB and ZBB from this matrix into this expression, I will get this impedance matrix, and this can be easily calculated. And once you get this expression, fault current, we have just seen that fault current will be inverse of this matrix multiplied by subtraction of voltages V1A minus V1B if the fault is occurring on A and B phase. So, this is how we can calculate fault current of phase A of 4th bus. So, in summary of today's lecture, we have seen LL fault. So, for LL fault we have derived fault current equations, and then we have seen the forced fault voltages equation. And to understand it better, we have taken one example, and this example will be was solved for LG, LLG and LL fault. Thank you.